Hi everyone, my name is Gohar, and along with Mohamad and Abdullatif, we will be presenting our project called Robot Teaching Assistant, a manipulation system for writing on the board. We will start by explaining the motivation and the project overview. In this work, we develop a full-stack robotic writing system. This includes three main modules: a perception system that detects the writing utensil, in this case a chalk, which has to be grasped for writing; a trajectory planning method to write different languages, phrases, fonts, and sizes; and finally, a hydroelastic interaction system between the board and the chalk to produce the ink on the board. This system has practical use cases in a classroom setting and can be thought of as a robotic teaching assistant that can write on the board. Below you can see the three main modules on a very high level. On the left, we show the perception of the chalk. By using a camera and the ICP algorithm, we determine where the chalk is and how to grasp it. In the middle, you can see the trajectory planning phase where the alphabet Z has been produced. This shows the polygon and the coordinates that we use to generate the polygon, which will be produced on the board. And last, you can see the KUKA EVA in action, where it is interacting with the board, and you can see the hydroelastic forces between the chalk and the board. We will start by explaining the simulation setup. For simulating our system, we use the PyDrake framework. We use the KUKA EVA robot, which is stationary and welded to the floor. We use the Shunk WSJ gripper for holding the chalk. We use a camera for perception of where the chalk is and to run the iterative closest point algorithm to get the appropriate gripper frame to grasp the chalk. We use the OBJ files along with their MTL files for the mesh of the objects for the table, chalk, and board. These files are converted into STF format for consumption in Drake.
For the perception system developed for our project, we plan to use ICP, and as we learned in class, ICP requires both a model point cloud and a segmented scene point cloud. For the model point cloud, we extracted the mesh information from the OBJ file of the chalk, and the resulting point cloud was sparse, which required us to interpolate between each pair of vertices to arrive at the resulting point cloud you see on the right. The second requirement for ICP is to have a filtered and segmented scene point cloud. And to extract the raw scene point cloud, we integrated a depth camera in our Drake implementation, which we used to extract the raw scene point cloud. The second step is we filtered faraway points based on the Euclidean distance from the center of the tabletop where we expect the chalk to be. Third, we used Ransack to segment the tabletop points from the chalk points, similar to an exercise we completed. And with that, we have the point cloud of the scene and the point cloud of the model, and we can apply ICP using an arbitrary initial guess. And as you can see in the figure, we arrive at a reasonably accurate estimate that we can use for the detection of the chalk in the environment.
Next, we will explain the details of the trajectory planning system. We want to develop a versatile system for trajectory planning capable of writing in multiple languages, phrases, fonts, and sizes. Abstractly, letters, numbers, and characters can be thought of as a collection of closed polygons. We can utilize the coordinates of the aforementioned polygons to represent trajectory on the board frame. We can simplify the trajectory by skeletonizing the polygon. Indeed, this method generalizes to multiple phrases and languages. We start with a text input, which could be an output from an object character recognition system. As an example, we use the letter Z and specify the font family to be cursive. Then, we convert the string to an image and generate a polygon that represents the letter in the image. Specifically, we use text-to-path and path patch from matplotlib to generate the polygon. We also have the option to interpolate in case we need to increase the number of keyframes. We also want to simplify our letter representation to have a simpler trajectory. To do this, we use polygonal skeletonization to extract the skeleton of the polygon as seen in the second picture. We then use connected component analysis to extract the connected components. We then loop through each connected component and extract the region of interest. We find the counterpoints of the region of interest by using OpenCV's find contours. We then fit a polynomial to the contour points. Finally, we perform necessary transformation on the y-coordinates to match our frame. Here are the results for different fonts. The first column shows a word with specified font. The color coding in the second column specifies a single polygon to be followed. The third column shows the simplified trajectories. After obtaining the trajectory, we post-process it into keyframes. This stage has some additional constraints like changing the axis between what Matplotlib uses versus what Drake is using, scaling up and down the trajectory based on the font to be displayed on the board, assigning appropriate transformation to words that needs to be split into multiple lines, and ensuring the characters are within EWA's reach and will not result in singularities, and considering the joint limits of the robot.
Finally, we will explain the details of the writing system. In order to produce ink on the board resulting from the interaction between the chalk and the board, we use hydroelastic force. The board has compliant hydroelastic, while the chalk has rigid hydroelastic properties set in their STF files. We use the appropriate mu dynamic for writing and mu static for making sure the chalk remains in the gripper. These properties are set for the board and for the chalk. We also set hydroelastic modulus to ensure enough contact, and we also adjust the penetration just enough to produce ink on the board but not break the chalk. This can be seen on the figure on the right. One output refinement process that we do is lifting the chalk while writing as a human would naturally do. Our initial version, shown on the left, writes the text, but the characters, more specifically the polygons, are connected to each other because the robot does not know when to lift the gripper from the board between the polygons. To eliminate this messy output, we add logic which allows the robot to lift after each separate polygon has been complete. This results in a much better output, shown on the right, and follows a similar movement pattern of writing as a human would naturally do. We also support writing in lines without the thick block font that we saw in the previous slide. This does not use polygons and uses line segments instead. To refine the output for this, we perform keyframe interpolation. In this case, the trajectory may not generate enough coordinates if you do it naively, which results in broken line segments when writing as seen in the image on the left. To refine this, we add logic to interpolate keyframes within each line segment, which results in much better, cleaner, and smoother line segments as shown in the image on the right. Now we will show you a demo of the final product in action. We will start by showing a thick block font example as the first demo. Here you can see all the pieces coming together and the robot writing in thick block letters the word Drake. You will first see the keyframes, and then we will remove the keyframes and you can see the robot writing and the interaction of the chalk and the board. Next, we will show the other mode that we also support, which is a single line font instead of the thick block. Here you can see the word Drake being written again, but instead it is being written using a single line flow and a composition of multiple line segments. Finally, we would like to thank Professor Russ and our TAs, especially Michael and Tommy, for all their help and support during this process. Thank you so much.